Hi everyone, today we are presenting our study of substitutability and price co-movement of copper and aluminum, a study on price fluctuation and demand interactions. We will introduce our research topic, following with literature review, data description, then our model selection, with finally regression analysis and findings. These are our fantastic group members, where we handle one part each.
Starting with our introduction, today we discuss the importance of copper and aluminum in electrical equipment and power transmission lines. These metals are crucial raw materials. Their price fluctuation greatly affect countries that rely on export and imports. Factors like emerging markets and technological change lead to price volatility. This volatility impacts supply and demand, influencing the global economy. It is essential to understand how copper and aluminum relate to each other. Price changes often result from demand shift, allow industry to substitute one metal for the other. This understanding can get better decision making in the industry. Our research focuses on the substitutability and price co-movement between copper and aluminum. We aim to understand how these factors impact supply and demand in the electrical equipment and transmission industries. Studying this substitutability is vital for reducing procurement risks and improving supply chain stability. We will use regression models to analyze historical price data and predict future trends. The report will cover the economic importance, methodology, and data analysis, culminating in practical recommendations for industry decision makers. This will help industries navigate price fluctuation effectively and make informed strategy choices.
In this part, I will discuss the critical role of copper and aluminum in various industries, focusing on their performance characteristics, market dynamics, and future research directions. Here are three important literatures. Copper is known for its excellent electrical conductivity, strength, and corrosion resistance. Copper is an important material for high-performance electrical applications. In contrast, aluminum, while less conductive, is lighter and more cost-effective. Market dynamics show the copper price has increasing due to the recent demand for renewable energy technologies. Aluminum price, however, tends to be more stable during the economic downturns. While aluminum can replace copper in some areas, but it cannot completely repair copper in power transmissions. Finally, current research often lacks a comprehensive view, focusing too much on short-term trends. Future studies should integrate economic, environmental, and technological factors to better understand the relationship between these two metals.
Our data comes from investing.com, a reliable financial platform. We use historical steady spot prices for copper and aluminum from CME, covering from 2014 to 2024. This includes opening, high, low, and closing prices in USD per ton. During the preparation stage, we focus on data cleaning and merging to ensure its consistency. First, we addressed mismatched entries by removing days where data was available for only one metal, keeping the dataset uniform. We also created a new column to count valid data points each month, which helps us track data quality and identify any gaps. After cleaning, we standardized ore prices in USD per ton for comparability. Finally, we noted a few limitations. Data for non-working days, such as weekends and holidays, is missing, and some factors like geopolitical events aren't fully captured. What's more, this graph shows normalized copper and aluminum price over time. From this visualization, we can see that both metals generally follow similar trend, reflecting differences in demand or market conditions. The graph suggests some level of substitutability, but each metal also responds to unique factors in the market. Therefore, we selected econometric models for further analysis.
For this project, we chose three models: ARIMA, VAR, and ECM models. The following are the resources for choosing these three models. We have 5 steps for economic models. The selection of models has been measured on the previous page. Non-stationarity of price series. The price series for both copper and aluminum are non-stationary. This means that their statistical properties, such as mean and variance, change over time. For ARIMA and VAR models, this non-stationarity is handled by differencing the series, transforming them into stationary process. Short-term and long-term relationships. The ECM model assumes the existence of a long-term equilibrium relationship between copper and aluminum prices dependent short-term diversions. Lunar dependence. Both VR and ECM assume that the relationship between copper and aluminum prices is lunar. Model suitability analysis. Each of these models of distinct advantage for our analysis. LIMA is suitable for capturing the independent behavior of each metal's process series, which is essential for understanding how copper and aluminum prices move individually over time. We are particularly useful for our study because it models this interaction between copper and aluminum prices. ECM is essential because it accounts for the long-term equivalence relationship suggested by our integration in tests. Economic significance of variables. Copper and analysis are crucial for understanding the cost structure in industries that rely on these matters. Lagged terms in both ARM and VAR models. Lagged price represents past market conditions that continue to influence trade price. The error correction term in ECM reflects the deviation from the long-term equilibrium between copper and aluminum price.
To fit ARIMA models to the aluminium and copper prices, we first ensured that several pre-fitting assumptions were met. We verified linearity, assuming that ARIMA captures only linear relationships, as well as stationarity by using difference data, which was shown to be stationary in our initial analysis. We also checked for seasonality by observing the data plots, confirming no clear seasonal patterns were present. Due to the complexity of the ACF and PACF plots, we used the auto-ARIMA function to select the optimal model based on the AIC, prioritizing accuracy by minimizing information loss. The aluminium model was selected with an ARIMA 212, and the copper model selected was an ARIMA 112. The selected models performed well, as shown by strong MSE, RMSE, and MAE results across a 1,000 data point rolling window with a one-step forecast. Residual analysis using the Box-Lung test indicated no autocorrelation, a positive sign for model accuracy. However, while not a strict requirement, the normal distribution of residuals is preferred. The QQ plot showed some deviation at the extreme, suggesting the residuals are not entirely normal. To address this, we applied an ARIMA Garch model with both models using a Garch 1.1. This better captured variance and improved residual normality. In practice, we recommend using the ARIMA Garch models due to the better residual performance and more accurate reflection of normality in the data. In fitting and assessing the ECM model for aluminium and copper prices, we ensured a co-integrating relationship between the two non-stationary variables, stationarity and non-autocorrelation in the error terms, and assumed linearity. Since both metals prices are non-stationary, we applied the Engel-Granger co-integration test. With a p-value less than 0.01, we confirmed a co-integrating relationship between aluminium and copper prices. Our linear regression and ECM model showed significant results for differenced copper price and lagged residuals, indicating that changes in copper prices drive about 15% of aluminum price changes. The model is effective during stable periods, but struggles with high volatility, which is reflected in the adjusted R-squared of 0.28 and residual standard error of 25.19. To address ECM limitations, we also fitted a time-varying ECM, which showed slightly improved performances with a pseudo R-squared of 0.31. This model adjusted slightly better to volatility with a residual standard error of 24.6. The residual still lacked homoscedasticity and normality. Residual analysis met ECM assumptions for both models, with no autocorrelation, as the Durbin-Watson test statistic of 1.97 and 1.98 respectively reflects no autocorrelation for both models. In applying the augmented Dickey-Fuller test, the residuals of both models demonstrated no autocorrelation with almost zero p-values. However, residuals lacked homoscedasticity and normality. We applied a vector autoregression model to analyze the short-term dynamics between copper and aluminium prices. This model allowed us to examine how past prices of each metal affect their current values, reflecting that fluctuations in copper prices have a lagged effect on aluminium prices and vice versa. The pre-fitting assumptions of linearity and stationarity had already been satisfied, enabling the application of the VAR model. The optimal lag period was determined by the VAR select package, with the information criterion of both AIC and BIC both recommending a lag of period 1. Our model fitting shows significant short-term interactions with a 1-period lag in aluminium prices positively impacting copper prices. This suggests that fluctuations in aluminium can drive short-term changes in copper prices, indicating that these metals may act as partial substitutes. The impulse response analysis further supports this, with a shock to aluminium prices having a quick but short-lived effect on copper prices, while a shock to copper prices cause a brief decline and rebound in aluminium prices within 3 periods. The VAR model scored poorly in regards to the R-squared contributing very minimally both ways in the long term, with F statistics just statistically significant. Hence, when applying the vector error correction model, the error correction term was statistically insignificant. This suggested that while there's a short-term influence between copper and aluminium prices, there was no stable long-term equilibrium relationship under the VAR and VECM models.
Firstly, through data analysis, we found a significant correlation between the prices of copper and aluminum in the short term. Through the VAR model, we see that changes in aluminum prices have a positive impact on copper prices, indicating a short-term price correlation between the two during demand fluctuation. The impact response analysis also indicates that the fluctuation of aluminum prices has a significant but short-lived impact on copper prices, which means that short-term substitution strategies can be utilized under specific market conditions. However, in the long run, the analysis results of the ECM model shows that the prices of copper and aluminum tend to be independent in the long run, indicating that their prices are not affected by each other in the long run. This also means that the long-term prices change of both are more driven by their respective market demands and external factors, rather than interdependence. Overall, copper and aluminum can replace each other in the short term, but in the long run, they are more suitable for management as independent resources. For industrial that rely on these two metals, it is recommended to adjust procurement strategies according to different time frame to effectively respond to market price fluctuations while maintaining supply chains stability.
That is our reference. Thanks for watching.